Okay, let's continue now with a pretty useful reaction, the Malonic Ester synthesis. Okay, with the synthesis, we're going to prepare carboxylic acid in the form of carboxylic acid with a CH2, an R group, or maybe two R groups on that CH right there, starting with diethyl malonate, CH3CH2O, C double bond O, CH2, C double bond O, O, CH2, CH3. Note this is a diester. And it's a malonic ester because we have the ester group here, carbonyl, CH2, carbonyl. Recall that's the malonic group. Also recall if there were two CH2s in between two carbonyl, that's succinic. Okay. So a little background first. The first thing to note is that if you have our two esters here and we add acid to it, well, that's just acid catalyzed hydrolysis of an ester, and we know that gives us alcohol, so we'll get two equivalents of ethanol, plus these two carboxylic acids, this malonic dicarboxylic acid here. Well, it turns out malonic dicarboxylic acids are unstable. And if you heat those up, you get this crazy reaction. It's a little crazy, and this is the mechanism of the reaction. Note you've got three things happening all at the same time. The oxygen-hydrogen bond of one acid breaks to become a double bond here. The carbon-carbon double break bond, or excuse me, the carbon-carbon single bond breaks here to make a double bond up here, and then this carbon-oxygen single bond, double bond, the pi bond breaks and attacks that hydrogen there, all at the same time. So the bottom part of this molecule, this becomes CO2. The top part of the molecule up here becomes CH2 double bond C. This is diol here. But note, it's not just any gem diol, it's a gem diol that's also an enol, and it'll tautomerize into the carboxylic acid. So, take home point, one of these carbonyl groups becomes CO2, the other will end up staying as a carboxylic acid. All right, and note, if you have a carboxylic acid and a ketone in a malonic type of situation, carbonyl, CH carbonyl, adding heat, this part will become CO2, and through this process of tautomerization, this ketone will stay. And so people looked at this and said, all right, this is nice. Recall, this is a little weird way to draw it, but if you have this malonic ester, ET stands for ethyl, ETO, ethyl, CH3CH2O, C double bond O, CH2, C double bond O, O, CH2, CH3. Recall that these two protons have a pKa of around 9. Yeah, these are fairly acidic protons in between those two carbonyls, pK about 9, so if you add a little ethoxide, that'll just deprotonate that to make this carbanion, and we've seen this before. This carbanion then can attack an alkyl halide through SN2, and we can end up putting that R group on this carbon right there. And so if we have this R group on that carbon, if we then hydrolyze the esters and add heat, we can end up with the R group on that CH2 of a carboxylic acid. So let's look at this. What can we do with this? Well, check this out. What would happen if we took our malonic ester here, added sodium ethoxide, followed by ethyl bromide? Well, sodium ethoxide snags one of these hydrogens to make the carbanion here. That carbanion then will attack this carbon right here, kicking off the bromine, so you can see we'll put this ethyl group right here on this carbon. Now, if we decide to hold off on our hydrolysis, we can do it again. Add another alkoxide here, ethoxide, with ethyl bromide, and we can see that, well, negative alkoxide here will take the other proton on this carbon, That carbanion will attack this. We'll put that second ethyl group on this molecule. So now we've put these two ethyl groups on that carbon that was alpha to both carbonyls. Now we can do our hydrolysis, add the heat to get rid of CO2, and we can just say, all right, hydrolysis kicks off those ethyl groups. These both become carboxylic acids. Heat takes this carboxylic acid, removes it as CO2. This carboxylic acid will remain after tautomerization. And so we end up with this carboxylic acid end here, and this has a CH, CH2, CH3, CH2, CH3. You put two ethyls on that guy and got rid of this as CO2. And note, hey, check this out. We can do an intramolecular malonic ester synthesis, starting with this beast here. And this looks like a nasty beast, but you can just buy this stuff. It's so useful. People make a lot of it. You can buy it. At our ethoxide, we can see that will make a negative charge here. Carbanion, which will attack this carbon, kicking off the bromine. So then to this carbon is attached this CH2, 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 Br. We add another equivalent of NaOET. That'll put the second negative charge on here, take off that second proton. And so, well, we got a negative charge here. We've got a good leaving group here. Then it will attack the other end. It'll attack this carbon. And we can see the whole trick is to count your carbons. We have this carbon here. 1, 2, 3, 4 carbons in this chain. So we have this carbon, 1, 2, 3, 4, and back to that original carbon to make this cyclopentane ring. Hydrolysis followed by decomposition with heat gives us our carboxylic acid and our cyclopentane ring. Okay, so question. Here's the molecule you want to make. Here's our carboxylic acid. Here's alpha to the carbonyl. We want a methyl and a 1, 2, 3, 4 and a butyl group on there. How would you think to make that? Well, buy this stuff. Add ethoxide to take away one of the protons here and make the carbanion. Attach the methyl group. Add another equivalent of ethoxide to take away this proton. Add the butyl group. Note this is SN2, so there's no rearrangements or anything. So the straight chain butyl group will go on here, hydrolyze, heat, and we get our carboxylic acid with the methyl alpha off the alpha carbon and the butyl off the alpha carbon. All right, and then someone said, well, hey, that's cool, but why do esters have to only have all the fun? Why diesters? What if we just have one ester on there? And so we came up with the acetoacetic ester synthesis. Acetoacetic ester? Did I stutter? No, check this out. Okay, acetoacetic ester. Okay, so if we look at this right here, if we got rid of this part right here and pretend that was a CH3, wouldn't this be an acetic ester? This would be ethyl acetate if that was a CH3 right here. If this was a CH3, this would be ethyl acetate that you see. So that's an acetic ester. And what did we add to this acetic ester? We added an acid group, CH3 C double bond O. This acid group was added to this acetic ester, so it's an acetoacetic ester. Acetoacetic ester. Okay. So if we start with this acetoacetic ester, a beta keto ester, if here's our ester carbonyl, alpha beta, the beta carbon to this carbonyl is a ketone, beta keto ester. We can attach more groups to this R group. We can attach more alkyl chains to this CH2 right here. We can attach one R group, we can attach two R groups using the same methodology we did with the malonic ester synthesis. So let's look at it. Start with our acetoacetic ester. What would happen at the series of this, look at this, at these 5 reactions. Add sodium ethoxide, then add this propyl bromide, then add sodium methoxide again, and then, ooh, look at this, C6H5CH2I, a phenyl ring with a CH2 and an iodide on there, and then add acid and heat. Well, hopefully you should be able in your head to work through it, but let's go through it anyway. All right, sodium methoxide makes us a negative carbanion. Propyl bromide is going to put this propyl group on this alpha carbon. Sodium methoxide takes off the second hydrogen here, making a carbanion at the same spot as before, which will attack this carbon, putting on this carbon a CH2 and a benzene ring. Acid does our hydrolysis to make this a carboxylic acid. Heat gets rid of this part as a CO2. Therefore, we'd expect CH3, C double bond O, and bonded to this carbon would be a propyl group and a CH2 and a benzene ring. So there we go. Alpha carbon has got our propyl group attached to it and a CH2 and phenyl ring. So note, just starting with this molecule that you can buy and some other nice friendly molecules, you can make this pretty big beast right there. Well, that's rather pleasant. So, our last thing right here, comparing various synthetic methods. Note, if we took acetone, going back a little bit in the chapter, and add LDA, CH3I, oh, this takes us back. Well, let's see, LDA, ooh, that's a very strong base, and we recall LDA is sterically hindered. It's going to snag one of these alpha protons right here to make the carbanion, and then that will attack, ooh, CH3I, and can we see we're just going to add this methyl group on to the end here and end up with CH3, C double bond O, CH2, CH3. Just snagged off one of these protons with LDA, making the carbanion, and then added this methyl group to that carbon. Note, what if we started with our acetoacetic ester and added sodium methoxide, and that would take off one of these hydrogens here, and then this guy would attack the CH3, so that would also put a CH3 right here, alpha to the carbonyls. Acid and heat, well, acid will hydrolyze this to the alcohol and the carboxylic acid. The heat will get rid of this as CO2. And so we just end up with CH3, C double bond, CH2, CH3, the same product. So here are two methods to make this ketone, this 2-butanone, if you love IUPAC. Which is better? Both will work. One might say, oh, you know, this is more steps and this looks more complicated and that's a more complicated molecule. But realize, you have to buy your LDA, you have to buy this. LDA is a very strong base. It doesn't ship well, you know. It's expensive also, and it's pretty nasty stuff. This is much cheaper than LDA, and sodium methoxide, well, that's cheap. We both have the CH3I, acid, hello, sulfuric acid, got that by the ton, and heat. So this method here, and note, you don't have to take your product and you don't have to isolate it after adding the CH3I. You can just throw in the acid and the heat. So without needing for isolation here, it turns out this bottom method is the better method to make this because it is less nasty for you, no LDA, and it's cheaper to do. But those are two ways of making that product. Okay, this ends the chapter. We will start looking at some aldol type reactions, more chemistry with carbon alpha to the carbonyl in the next video.